What is up, guys? Welcome to Barton. My name is Heinrich, and today we're going to take a look at how we can give our enemy some more complex behaviors using our finite state machine. So as you can see, our little red guy here on the left can move left and right, and then if we come in range and he sees us, he will detect us and then charge at us. And then if he gets close enough, he will swipe at us and actually hit us. And of course we can hit him, and then we can eventually stun him and kill him. And we're also going to see how we can use the same principles to make another enemy and make it so our code is very expandable, and then we can reuse a lot of it to create multiple enemies. So this enemy here can shoot at me when he sees me. If I get close, let him get a little bit closer to me first. But if I get close to him, he will jump away before shooting at me. And adding all these different behaviors to the enemies is really simple. So let's head to our project and see how we can do this. So this is what the game looked like where we last left off. We have an enemy that can move left and right, and it'll detect the ledge and just turn. Now the way that we've been doing this works, but it's actually really bad and really inefficient. And let me explain why. We have this basic enemy controller script in which we have a bunch of different functions for all the different states that we have, including our enter, update, and exit functions. But this makes it really difficult to add new states to this enemy or to reuse the script on different enemies where we want different states. So what the goal of this episode is to extract this state machine system from the enemy code and make it into something that we can reuse on a bunch of different enemies. To do this, we're going to use something called inheritance. Inheritance basically allows us to define a base class that has certain variables and functions, and then define classes that derive or inherit from that base class. These derived classes will get all the variables and functions from the base class with the option to override the base class functionality if we want to. Take, for example, this enemy class. In it, we will write the variables and functions that all enemies should have. So we can have something like health and movement speed. We can also define functions all enemies should have. For example, all the enemies should have a function to move, and all the enemies should have a function to take damage. Now we will make two new enemy classes that will inherit from this base enemy class. Let's say one is a skeleton and the other is a mage. In both the mage and the skeleton, we can now set the respective health and movement speeds without having to redeclare those variables, as they have already been declared in the base class. They will also both have the ability to move based on their movement speeds and take damage. But we also have the ability to add to or completely change the functions from the base class we are derived from. While this may seem like a lot of extra work when making one enemy, if you're planning on creating a bigger game with many different enemies, this is a very powerful thing that we need to understand. If you feel like you need to know more about inheritance, I will link some good tutorials in the description. So we're not going to be using the basic enemy controller script anymore. Instead, let's start working on our finite state machine framework that we're going to use. In our enemies folder, let's start off by creating a new folder, and we'll just call it state machine. Inside this folder, we can then create 3 new C# scripts. The first one we're going to call state, and we can just open that up so long. The next one is going to be called finite state machine. And the last one is going to be called entity. So entity is going to be our base script for all our enemies, and all our enemies are going to inherit the entity class. The finite state machine class is going to take care of keeping track of what state the enemy is currently in, and then run the correct code from that state. To do this, we're going to make use of a state class that is going to have all the functions that every state should have. So our enter and exit functions, our normal update function, and our physics update function. When we create a state, for example, an idle or a move state, those states are going to inherit from state. Then in our enemy classes, we're going to create objects of those states and use our finite state machine to keep track of which state we are currently in. So let's start with our finite state machine script. We can delete all of this pre-generated code as we will not need it, and we can also get rid of this mono behavior. This means that the finite state machine script is currently inheriting from mono behavior, which is something that we don't need, as the script is not going to be attached to any game object. So we can just get rid of it like that. So the first thing our finite state machine script needs to do is keep track of the current state. So we'll create a public state variable that we'll call current state. Now after this, we're going to put a squiggly bracket, and then we're going to say get semicolon, and then private set semicolon. This is basically just shorthand for having a getter and a setter for this variable. This means that this variable is public to get, so any other class can get what this variable is, but this variable can only be set within this class. After this, we're going to write a initialize function that is going to take care of setting the first state when the game starts. So it'll have an input parameter of type state that is our starting state. Now inside the initialize function, we need to set our current state equal to starting state. And then after this, we're going to call the enter function on our state. Now we haven't written these functions yet. So let's head over to our state class and declare all the functions we're going to need there. So in the state class, we can start off by deleting all of the pre-generated code. And this also does not need to inherit from mono behavior. Let's start off by declaring all the variables the state needs to keep track of. The first thing we want the state to keep track of is the finite state machine that it belongs to. So we'll create a protected, and what protected is it's basically private, but any class inheriting from this class also has access to this variable. So protected finite state machine, and we're just going to call it state machine. Next, we also want this state to keep track of which entity it belongs to. So we'll say protected entity, and we'll just call it entity. Next, I want the state to also keep track of its starting time. So when did the enemy enter this state? So we'll say protected float, and we'll just call it start time. Now, seeing as we are going to be creating objects out of these states, we need to create a constructor. So for this, we just need to say public and then state. So this has to be the same as the class name. And then in brackets, we're going to take in all the parameters that need to be given to the state when we create it. So the first thing is entity. So when we create this state on our enemy class, it'll pass itself through as the entity, and the state will know, okay, this is the enemy that I belong to. Next, we also need to pass through the state machine. So finite state machine, and we'll just say state machine again. And that is it for now. Now we can just open up some brackets, and inside of this, we can set the variables that we just created. Now, because we have the same names in the input parameters and as our class variables, we need to say this.entity to refer to this entity, and then we can set it equal to the entity that we passed through. And then we can say this.stateMachine equals stateMachine. Now we need to write the enter, exit, logic update, and physics update functions. So we'll say public, and then we're going to use the virtual keyword, which just means that this function can be redefined in the derived classes. And this function is going to be void, and we'll call it enter. And then next we can do the same thing for our exit function. And then next our logic update function. And then finally our physics update function. So in our state class itself, we're not going to put much inside of these functions, as each of our different states is going to have different behavior within each of these functions. That's the whole point of this. But there is something that we want every state to do, and that is keep track of its start time. So in the enter function, we can start off by saying start time equals time.time. So that means every time that this enter function gets called on whatever state it is, it's going to store the start time. And then in any of our states, we can reference this start time without having to set the start time in each of our states. I hope the power of inheritance is starting to become a little bit more clear now. If not, just hang on. It'll make sense once we start creating the different states. Now, if we go back to our finite state machine script, in our initialize function, we can now say current state dot enter, meaning when we initialize the state machine, we set the current state to whatever state, and then we call the enter function on that state. Now, I hope you can already see how much better this is than the way we were doing the state machine previously. Before, in our update function, we had a switch case statement that would check the current state against all the different states the enemy has, and then call the correct update. So every single frame, we had to check this current state against all the different states. Meaning if we had 20 states, it would have to do 20 checks every frame, and then if we had 100 enemies, I think you can see how the amount of checks we have to do adds up. Whereas in this case, we don't have to do any checks. So this is going to be a lot more efficient and allow us to expand our enemies so much faster. Next, we need to make a function so that we can change the state that we are currently in. So let's create another public void, and we'll call the function change state. And this is also going to take in a state parameter, and we'll just say new state, like that. And now what we can do is we can call the exit function on our current state. So current state dot exit, like that. And then we can switch our current state to our new state. Current state equals new state. And then we can call the enter function on our new state. So we can just say current state dot enter, like that. And now we have changed our states. This is all we need for the finite state machine script, so we can close this. Next, we need to take a look at our entity script. In this case, entity is going to derive from mono behavior. Even though entity itself is not going to be directly put on a game object, the different enemy classes that derive from entity are going to be put on those objects. But we can just start off by getting rid of this code again. Now we need to think of what are some things that each and every single one of our enemies is going to have. The first thing that comes to mind for me is that all of our enemies are going to have a rigid body 2D. So we can start off by declaring a public rigid body 2D, and we'll just call it RB. And then we'll do the same thing where we say get and private set. Seeing as we may want to reference the rigid body from our states, but we only want to be able to set it in our enemy class. Next, all of our enemies are going to have an animator. We'll just call it anim, and we'll do the same thing. And another thing all of our enemies have is an alive game object. Because if you remember how we set up the enemies, we have this enemy1 game object, and then we have an alive game object underneath it. Just in case later on we want to make it so that when the enemy dies, it'll break into different chunks that we can throw around that have physics. For now, we just have the one alive game object. So we need to keep track of that as well. So we can have a public game object that we'll just call alive game object. Get private set. Okay, now let's write the start function for the entity. In this case, our start function also has to be public virtual void, like that, so that our other enemies can override it in case we need to add things to the start function. And then in the start function, we can just start off by getting the references to these three components. So let's get the alive game object component first. So we will say alive game object equals transform dot find, and we're looking for the alive game object, and we just want to return the game object, like that. Next, we can get the rigid body from the alive game object. So we'll say RB equals alive game object dot get component, and we want the rigid body 2D component. And then we can do exactly the same thing for the animator. So alive go dot get component animator. Cool, and we can just save it there. Now that we have the animator component reference, I actually want to head back to the state class. And for every state, I want to give it an animation Boolean name so that each state can take care of setting the animation parameters by itself. So let's start off by actually declaring a protected string. And this string is going to be called anim bool name. And then we'll just add this as a parameter to our constructor. And then set it the same way. Now what I want to do is in the enter function, I want to reference the animator on our entity. So I will say entity, which is being kept track of, dot anim, which we can get because we have a getter for our animator. And then I want to say dot set bool, and the Boolean name is going to be anim bool name, and the value is true. We can then just copy this and paste it in our exit function and set it to false. That means for our different states, we don't have to care about setting the animation parameters true or false. We can still add more parameters if we need to, but the base parameter is going to be there. We just have to supply it with a name and make sure that the name in our animator matches the different states. And now we're actually done with the state class, so we can close this as well. So now before we head any further with the entity class, let's start looking at some different states. So let's head back to Unity, and we're just going to try and get back to where we were before, having a move state for the enemy, but then we're also going to add in the idle state. So let's head back to our enemies folder, and let's create a new folder that we'll just call states. And then inside our states folder, we'll create another folder that we'll just call data. So seeing as our different states are going to have different parameters like idle time and move speed or things like that, and the fact that the states are just going to be objects that we create in code, so we can't set those parameters in the inspector, we're going to make another set of scripts out of scriptable objects to hold the data for the different classes. So in our states folder, let's just create our idle and move state scripts. So the first one is idle state, and the next one is move state. And then we can just open up both of these in Visual Studio. And just while we're here, let's go into the data folder and let's create 2 data scripts for each one of those states. And so what I like to do is I like to start off the name with a capital D underscore, just so that it's easy to distinguish. And the first one is idle state. And then the next one is move state. Like that. And then we can just go ahead and open up both of these in Visual Studio as well. So starting with our move state, we can get rid of this code again. And now instead of inheriting from mono behavior, we're going to inherit from state. So now this means all the variables in state and all the functions in state we have access to from move state. The first thing we need to do is create a new constructor for this state now. To do this quickly, we can just click on our move state name up here, and then on Windows hit Control and then full stop, and it'll bring up this little drop down. At the bottom we can click on Generate Constructor, and it'll add all the parameters that state has already. Now after the bracket here, you can see we have colon and then base, entity, state machine, and anim bool name. Basically what this means is it's going to pass the entity, state machine, and animation variables that we get when we call this constructor on to our base class, which is state. So now if we want to add anything else to the constructor, we can go ahead and do that. We want the move state to have a reference to its data class. So we can start off by declaring a protected, and we want our move state, and we'll just call it state data, like that. Now in our constructor at the end, we can add a move state data type called state data, And then in the constructor, we can then just again say state data equals state data. But this actually has to be this dot state data. So this state data equals this state data. Now, if we want to override a function from our state class, we do it like this. We start off by saying public override, and then the function that we want. So if we want to override the enter function, boom. Now, as you can see inside of this function, it automatically added base.enter. This means that when this enter function gets called, it's going to also call the enter function in our base class, which is state. Usually we want this, but say we want to completely change the functionality of a state, we can just remove this base.enter and the code inside of our state base won't get called. But this is fine. We want it like this. Now, if you also want to quickly create all the overrides, you can come back up to move state and then hit Control full stop again, and then say generate overrides. In this list, we can select all the functions whose overrides we want to generate, and we do not want equals, getHash, or toString. Just these three functions that we created in state, and enter we already made. Then just click OK, and you can see it added all the overrides for us. Now in the state class, we can take care of setting the velocity of the enemy to make it move. So let's head to our dMoveState file, and let's get rid of this code. And now this time, instead of inheriting from monoBehavior, we're going to change this to Scriptable object. So what is a Scriptable object? Well, according to the Unity documentation, a Scriptable object is a data container that you can use to save large amounts of data independent of class instances. So basically what we're going to use this for is to store all the variables related to our move state. And then we can create different files from this dMove state for each of our different enemies that have a move state. So in here we can start off by just defining, say, a public float that we're just going to call movement speed. And you'll see just now how we're going to be able to change this movement speed in the inspector. But just as good practice, let's start off by giving it a default movement speed of 3. Now if we go to our move state, you'll see that we can access this movement speed variable by saying something like state data dot movement speed. There we go. So in our move state, when we enter the state, we want to start moving the enemy. So we can do something to set the velocity of the enemy. But we want every enemy to be able to move. So what we can do is we can go back to our entity class and create a function that takes in a movement speed and sets the velocity of the enemy. And then we can just call this function from our move state. Now before we do this, there's some more things that we have to add to entity first. First, our entity has to have a state machine. So at the top, let's declare a public finite state machine. And we'll also just call it state machine, like that. Then in our start function, we need to say state machine equals a new finite state machine. Like that. So now every entity is going to have its own state machine that is an object of finite state machine. Then we just need to create our update function. So public virtual void update, like that. And then in our update function, we need to say state machine dot current state dot logic update. So every time update gets called on our entity, we're going to call the update function on our state. And then we can do the same for our fixed update. So public virtual void fixed update, and then state machine dot current state dot physics update. Okay, now let's write our velocity function. So we'll just call it set velocity. So we'll make another public virtual void. We'll call it set velocity. And this is going to take in a float that we'll just call velocity. Now in this function, we're just going to set the velocity of the enemy based on its facing direction and the input velocity. So let's come back up to our variables. Let's declare a public int called facing direction. And for this variable, we're also going to say get and then private set. We're not going to do this for all variables. We're just doing it for the ones that we might want to get access to in our states. So maybe in our movement state or in our idle state, we want to know what direction we're currently facing if we want to do something. So if we create a getter for it, we can do that. Next, I'm just going to declare a private variable, and it's going to be a vector2, and we're just going to call this velocity workspace. And we're just going to use this whenever we want to create a vector2 that we need to set somewhere. So instead of creating a new vector2 every time, we're just going to change the values of this workspace. So in our set velocity function, we can start off by saying velocity workspace dot set, and then for our x, we're going to specify facing direction multiplied with velocity. And then for y, we want to set it to rigidbody.velocity.y. And then after this, we want to say rb.velocity equals velocity workspace. So this will now set the velocity of our enemy. So back in our move state, when we enter the state, we can just say entity, seeing as set velocity is going to be a function available to all of our entities, dot set velocity. And then as our input parameter, we can go look at our state data and pass our movement speed, like that. Okay, so now we need to make it so that the enemy can detect ledges and walls again, just like before. Again, this is probably something that we want all of our enemies to be able to do. So we're again going to write functions in our entity class. So in our entity class, underneath our set velocity function, let's create two more functions. Public virtual void, and the first one is going to be called check wall. And the second one is going to be called check ledge. Like that. Now let's think of what we actually need to do this. To check for our wall or our ledge, we first need a position to check from. We need a distance that we need to check, and then we also need to know what we're checking for. So let's come back up to our variables, and let's create a serialized field private transform. And the first one is going to be a wall check transform. And then we also need a ledge check transform. Like that. Now, instead of storing the distances for the checks here as a variable, we're going to do the same thing as we did for the states, where we create a data file. So let's head back to Unity, and let's create another C# script that's going to be d underscore, and we'll just call it entity. And we can then open that up, delete this code, and make it inherit from Scriptable object. So the first thing we want is a public float called wall check distance, and then a public float ledge check distance. We can actually also create a public layer mask, what is ground. Then back in our entity script, we need a reference to this data. So this will be public d underscore entity, and we'll just call it entity data. Like that. This does not need to be set by a constructor, as we're just going to set it in the inspector when we add the enemy script to our enemy. We can come back down to our two functions, and these functions are actually not going to be void, they're going to be bool, because we want them to return whether we are detecting a wall or not. So inside the function, we simply need to say return and we are returning physics2d dot raycast. And for the check wall function, we are raycasting from wallCheck.position. The direction is going to be a live game object dot transform dot right, and our distance is going to be entity data dot wallCheck distance, and then finally our layer mask is going to be entity data dot what is ground. And then in our check ledge function, we can do the same. So change it from void to bool, and then say return physics2d dot raycast. And this time it's going to be from ledge check dot position. The direction is going to be vector2 dot down. The distance is entity data dot ledge check distance. And then finally, our layer mask is entity data dot what is ground. So now back in our move state, we can create two protected bool variables that's going to store whether we are detecting a wall or a ledge. So the first one is going to be is detecting wall, and the second one is detecting ledge. And now we can use this in this state for our decision making. So when we enter the state, we want to say is detecting ledge equals entity dot check ledge. And then we also want to say is detecting wall equals entity dot check wall. So when we enter the state, it's going to check for these two things, and then we can also just copy it and then paste it in our physics update. So every time fixed update happens, our enemy is going to check, is there a wall in front of me and is there a ledge in front of me? Now changing from the move state to the idle state isn't going to happen in the move state script. Instead, we're going to make another script that's going to inherit from move state for our specific enemy that is just going to use these parameters to determine if it should change to a different state. This is what's going to allow us to have different states on different enemies without all the enemies having to have all the states. So before I show you how to do that, let's create the idle state, and then after that we can make it work for the enemy that we currently have. So let's come to our idle state class, and let's actually bring our d_idle state class next to it so we can change between them quickly. And in our idle state, let's delete all this code that we do not need, and then make it inherit from state. We can then come and create the constructor with control full stop. And we also want to add the data to the constructor. So we have a protected d_idle state that is called state data, like that. Add it to the constructor. And then set it. So this dot state data equals state data. And then we can create all the function overrides by clicking on idle state, control full stop, generate overrides. Again, we don't want equals, we don't want get hash, and we don't want toString. Now, how I want the idle to work is when we enter the idle state, we're going to choose a random time between a min and a max that we're going to idle for, and then we're going to move back to a different state depending on the different conditions. So for now, we're just going to change back to the move state. And in this case, seeing as I'm either going to be by a wall or by a ledge when I enter the idle state, when I leave the idle state, I want to flip the character. So let's first start off by going to our entity class and writing our flip function. So it's going to be public virtual void, and we'll just call it flip like we always do. Inside the flip function, we'll start off by saying facing direction times equals -1, and then alive go.transform.rotate, and then we'll rotate it 0 on the x, 180 on the y, and then 0 on the z. So we can call this function from any state if we want to flip the enemy. So in our idle state, say I don't want to flip after the idle is done. So say the character has been moving in a straight line for a certain period of time and it just goes to the idle state, even though there's nothing blocking its path, and it just wants to keep walking straight. So we'll add a Boolean parameter to our state to make it so that we can choose if we want to flip when we leave the state or not. So we'll create a protected bool that we'll just call flip after idle. Now, because this is probably going to get determined by some conditions in other states, we must create a setter for this Boolean. So at the bottom, I'm just going to create a public void set flip after idle, and it'll take in a Boolean that we'll just call flip, and then inside this we'll say flip after idle equals flip. Now, when we enter the idle state, we want the enemy to stop moving. So in the enter function, we will say entity.setVelocity to 0. Next, we need to determine that random idle time, which means first we need a min and a max idle time. So let's come to our idle state and get rid of this code, make it inherit from scriptable object. And the first thing we need is a public float min idle time, and then we need a public float max idle time, like that. So in our idle state, let's create a protected float to keep track of what the idle time is that we're going to use. Call it idle time. Let's actually create another function. This time it's going to be a private void set idle time. Actually, we'll make it more descriptive and say set random idle time. And basically what this function is going to do is just set idle time equal to random.range. And for our min, we will use state data.min idle time and state data.max idle time. Now, in our logic update, we're going to keep track of whether or not we've passed our idle time. So should we now transition back to another state? So we'll actually create another bool to keep track of if we are over that time or not. And we'll just call it is idle time over. When we enter the idle state, we need to set this to false. So is idle time over equals false. Then we need to set a random idle time. And now in our logic update, we can come and say if time.time is greater than or equal to our start time. And remember, start time is a variable that every single state has because we declared it in our state class. So time.time is greater than or equal to start time plus idle time. So if this is true, we'll just set is idle time over equal to true. Again, we'll take care of actually transitioning to our different state in a different class. But now the last thing we need to do for the idle state is in our exit function, we'll come and say if flip after idle. So if this is true, then entity.flip. So when we leave the idle state, we will flip the enemy if flip after idle is set to true. Okay, so now we can come and make this work for the enemy that we currently have. So let's head back to Unity and head back to our enemies folder, and let's create a new folder. This time we're going to call it enemy specific. And in this folder, we'll create another folder. We'll just call it enemy1. This is just to help keep it organized when we start creating our second enemy. Now, in this folder, we're going to create a new C# script. And this time, we're going to start off by saying E1 to mean enemy1 underscore, and we'll create a idle state. And let's do the same for the move state. So E1 underscore move state. And let's open both of these up in Visual Studio. Starting with our move state, let's delete this code and then make it inherit from our move state. So E1 move state is now inheriting from move state, which means it's also inheriting from state. So it receives both the properties from state and from move state. This also means we need to create a new constructor for it. So we can just generate constructor. And now one thing that we want our E1 move state to do is keep track of which enemy it actually belongs to. So we're already keeping track of which entity it belongs to, but because we're defining which states the different enemies have in different enemy classes, we need to know which enemy that is so that we can transition to those states. So we actually need to come back to Unity and declare another C# script that we're just going to call enemy1. Let's open this up as well, and this time make it inherit from entity. And we'll just leave it like this for now and head back to our E1 move state. And let's get a reference to our enemy1. So we'll have a private enemy1, and we'll just call it enemy. And then in our constructor, we can add enemy1 enemy. And then we say this dot enemy equals enemy. And now let's also get all the overrides. So generate overrides. Only the last 4. And now in here we can specify where we want to transition to based on our conditions. So in our logic update, we're going to say if is detecting wall or not is detecting ledge. So we have either walked up against a wall or we are at a ledge. Then we want to go to our idle state. Now, because we have not yet defined idle state in enemy1, we can't do this yet. So let's just leave a little comment here for us to remember that we have to come back to this. So if we say to do with a colon and then say add transition to idle, if we come at the bottom and look at our task list, we can see that our to do has been added here. So that means we can always click here and come back to this later if we have forgotten. So that we can make this work, let's actually go back to our enemy1 class. And let's start off by defining all the different states enemy1 is supposed to have. Now, seeing as we only have idle and move for now, those will be the first 2 that we do. So first we'll have public E1 idle state. And we'll just call it idle state. And for this, we'll do the same get private set as we've done before. And then next we need a public E1 move state called move state get private set. And then next we need to have references to the data for the different states. And in this case, they're going to be serialized field private objects. So the first one is d underscore idle state, and we'll just call it idle state data. And the next one is private d move state. And we'll just call it move state data. Now next, we need to override our start function. So we'll say public override start. And in the start function, we now need to create the objects for these states. So let's start off by creating our move state object, seeing as we haven't actually done the E1 idle state code yet. So we'll say move state equals a new E1 underscore move state. And to the constructor, we pass this as the entity, state machine as the state machine, and the animation Boolean name is just going to be move. And you'll see how this comes into play in just a second. Next, we have the move state data as our state data, and then this as enemy1. So now you'll see when we go back to our E1 move state, when we want to transition to our idle state, all we have to do is say state machine dot change state. So seeing as all the states have a reference to the state machine for the enemy, we can just call it directly from here, call the change state function, and then pass it the state we want to transition to, which in this case is enemy.idleState. This is still going to give us an error here, seeing as we haven't set up the E1 idle state yet. So let's go ahead and do that. Just delete all of this, make it inherit from state, get the constructor going. So control full stop, generate constructor. Let's get the reference to our enemy1. So private enemy1 called enemy. Add that to the constructor. Set it, and then generate the overrides. Like that. And so back in move state, our error is now gone. Whoops, idle state needs to inherit from idle state, not state. Now the last thing we need to do in our E1 move state is, before we transition to idle state, make it so that we'll flip after the idle state. So we'll say enemy.idleState.set flip after idle to true. So this means we're going to look at the enemy we're attached to, go to the idle state for this enemy, and set and call this function from that state. And that's it for the move state for now. We'll come back to this later when we want to make it so that the enemy can detect the player. But for now, it's done. Now in our idle state, it's going to be very simple. All we need to do is in logic update, say if is idle time over, I want to transition back to move. So we can say state machine dot change state, and I want to change to enemy dot move state. And that's all we do in this script. So we're just about ready to start setting this up on the enemy in Unity itself. The last thing we need to do is just come to our data classes and make it so that we can create those data objects in Unity. So this is something that Scriptable object allows us to do. And what we can do is, before we say public class, we say square bracket, create asset menu, normal bracket, and now we can specify a file name, which for this one I'm just going to say new entity data. And then next we can specify a menu name, which is basically the path that we can follow to create this item. You'll see how that looks now. So we can actually specify a path here. So I'm going to start off by saying data / and this is going to be of type entity data. And I'm just going to call it base data, just in case we want to create more data files for different enemies higher up the chain. So we can actually just copy and paste this to our other data classes. And so for our move state, I'm going to change this to new move state data. And this time the path, instead of being in entity data, I'm going to change this to state. And we'll say move state, like that. Now let's just copy this again and go to our idle state. Paste that in there. Change this to new idle state data. And change it to idle here. Okay, back in E1 idle state, because I made a mistake and made it inherit from state when I generated the constructor, we have a little mistake here. So idle state actually wants its state data before enemy1. So here, let's just say d_idle state called state data. And then we can come to this base part here and just pass it along. That should take care of any errors. Okay, so let me show you what this did. If we go back to Unity and we go to our project view and then right click create, at the top here you can see we've added this data part. And then if we click on it, here we have entity data and state data. So we can now click on any of these to create a data object. In this case, now we have a new entity data. And then if we click on it, we can set the different variables here in the inspector. So let's actually just delete this one for now. And I just realized I forgot to set default values, which is, like I said, good practice. So let's head back to Visual Studio again. And I want to set the default wall check distance to 0.2f, the default ledge check distance to 0.4f. Movement we did set, and then in idle, I want the default min idle time to be 1 second and the max to be 2 seconds. And that should be all of it. Okay, so now let's see how we need to set this up on our enemy to get this working. So let's head back to Unity and let's click on our enemy 1. Let's get rid of this trashy basic enemy controller script. And let's add our new and improved enemy 1 script to it. As you can see, we now have slots for our entity data, our wall check, our ledge check, and the data for our 2 different states. So let's just start off by dragging in the wall check and the ledge check, which I see I named ground check. So let's fix that. Ledge check like that. Drag that on there. And now for the data. So in our enemy specific enemy 1 folder, let's create yet another folder and we'll just call it data again. In this data folder, and then we can right click and say create data, entity data, base data. We'll say E1 underscore base data like that. And now let's create the state data. So data, state data, idle state. E1 underscore idle state data like that. And the same for the move state. Like that. And like I said, this might seem like a lot of extra work, but trust me, once this is all set up, it's going to make it so much easier to add more enemies to the game that have different behaviors. So let's click on our enemy 1 game object again and just drag in the base data into entity data, idle state data into idle state, and then move state data into move state. Now we are almost ready to see this in action. The last thing we need to do is set up the animator for the enemy. So let's go to the animator. And before, we already set up the walk animation and the hurt animation, but I'm actually going to just recreate these because I now have a complete sprite sheet to give you guys. So let's go to our sprites folder, enemies, and we can just delete this enemy 1.2 sprite file, and then we can import our new enemy sprite sheet. We can set the pixels per unit to 16 like we always do, change the sprite mode to multiple, filter mode to point no filter, and the compression to none, hit apply, then click on sprite editor, slice, grid by cell size 64 by 64, slice, hit apply, and now we have all the enemy sprites that we need. Let's pull up our animation window, click on our alive game object, and we can delete all these sprites in our walk animation. Let's actually click on scene so that we can see our enemy. And now enemy 1, oh, I saw a full stop there at the end, which shouldn't be there. I'll fix that for you guys. Anyway, enemy 0 to 7 is our walk animation. Perfect. And then we're going to create a new clip in animations, enemies, and we'll call it enemy 1 underscore idle. Change the sample rate to 15. And now sprites 8 to 11 should be our idle animation. As you can see, that's a little bit fast, so let's just pull this so it's 2 frames per sprite. And now just copy and paste this last sprite so that one also lasts 2 frames. Cool, so now we have an idle and a walk animation. So now we can just put away our animation window, and if we go to our animator, you can see we have our idle and our walk animation. I'm just going to get rid of the hurt animation for now, as we no longer need it. And I'm also going to get rid of the knockback parameter. So now we need to create 2 parameters, one for each state, and it needs to be called the same thing as we call it here in enemy 1 move Oh, I forgot to create the idle state. So let's say idle state equals a new e1 underscore idle state. This state machine idle, and then idle state data, this, like that. So now we have our idle state. And there's actually another thing I forgot because I'm not very good at this, and that is we need to initialize the state. So we'll say state machine dot initialize, and we want our first state to be our move state, like that. Okay, now we're done with the scripts, I think. Anyway, if we head back to Unity now, as you can see, our first animation is going to be our walk animation. We can then create our two parameters. So they're both bools. The first one is called idle, and the next one is called walk, I think. Nope, it's called move. Like that. And then we can make a transition from walk to idle. Click on the transition, make it so it has no exit time, and the transition duration is 0. We then have two conditions. One is that move is false, and the next is that idle is true. We then make a transition from idle to walk, set has exit time to false, transition to 0, and then the two conditions. The first is idle is false, and the next one, move is true. So now if we head to our game and run it, it should work. As you see, we can currently not see our enemy. So if we just head to our alive game object, you can see our default sprite is missing. So let's just add that back in and just use the first sprite like that. Okay, so now if we run it, you can see we're idling and we're turning, but we're not moving. So why is that happening? I think maybe it's just an issue with our ledge check and wall check offsets. So let's actually go to our data files and just make sure that what is ground is set to ground. That is something we did not set. And we have these distances. These distances might not be enough. So let's make it so that we can see those rays. So let's just go back to Visual Studio and go to our entity class. And let's call the onDrawGizmos function. Like this. And then we'll just say gizmos.drawLine, and we want to draw a line from our wallCheck.position to our wallCheck.position plus a vector 3, and this vector 3 is actually going to be vector 2.right multiplied with facing direction multiplied with entity data dot wall check distance. So what this is doing is it's drawing a line from wall check dot position to the right, if we are facing right, the distance of our wall check. And then next we can do the same for our ledge check. So gizmos dot draw line from ledge check dot position. And this time it's just going to be ledge check dot position plus vector 3 again, but this time it is vector 2 dot down multiplied with entity data dot ledge check distance, like that. And this, instead of being private void, is actually supposed to be public virtual void. Now we actually also need to remember to set facing direction equal to 1 in start. So I need to say facing direction equals 1. But because facing direction doesn't actually get set to anything until start gets called, this is going to be 0, so we won't be able to see the wall check distance in here unless the game is running. Go to scene, there we can see our wall check. Now this is actually supposed to be 0.2, like that. So now we have one last issue. As you can see, when we run the game, the character's idling, he starts moving, he moves for a little bit, but then he just stops. And that's because under our rigid body, we actually need to set a physics material which will just be the same as our player material, which is just a material that has 0 friction. And then if we run it now, you can see the enemy turns and then moves, stops at the ledge, turns, moves, stops at the ledge. And so now we can tweak all of these parameters from these data files. If you're wondering why he's starting out with idle instead of move, it's just because he's placed a little bit too high here. So when the game starts, he doesn't detect a ledge. So we can just move him down a little bit. And you'll see when we start it now, he will move and everything works perfectly. Now, I hope that wasn't too much to take in. If I forgot to explain anything, please reach out to me either in the comments or in Discord. This is quite a lot for me to keep track of, but I hope all of this will make sense as we keep going, and you'll see the benefit of doing it this way once we start adding more states, and then you'll definitely see the benefit when we make the second enemy, and you'll see how easy it is to add more enemies using this code, and how much we can reuse this code. So we're basically back to where we were before. I'm going to stop for now. So we're basically back to where we were before now. So next we're going to make it so that we can actually damage the enemy, and so that the enemy can detect us, run at us and try and damage us. But I think that's enough for now, so you can just let this state machine stuff stew a little bit, and then we'll head on to the rest of the states really soon. I have all of this worked out already, so we can get there really quickly. I hope you guys managed to learn something new from this video. And like I said, if anything was confusing, please reach out. I am more than willing to explain what's going on. So I would just like to thank all my supporters and wonderful people on Patreon, and a big thanks to Lewis for your support on Patreon. I hope you guys all have a wonderful day.